on hold, at least until I got out of the Navy. On the other hand, Jerry somehow managed to earn a PhD in engineering at Berkeley. Within the 4 years, he was teaching full-time at the Nuclear Power School. An amazing accomplishment. And then the rest of his career has been very amazing. He, after a few temporary positions, he joined the faculty at UCLA, where he's been ever since. He's had a long line of excellent students who now have very successful careers for themselves. I just don't have time to go through all the accomplishments. He's chaired many committees, many working groups. He's been involved in many NASA missions, editors of journals, published hundreds of papers. He, in 1975, when I was still teaching in the Navy, Jerry won a McElwain Medal, and you probably know that he's also this year's Hess medalist. But I think one of the strengths Jerry has had has being able to identify good problems and define them well, and then to persuade other people to help work on them with him. Anyway, that's how I got into the business, actually. When I first met Jerry, my research was numerical simulations, but it was in solar physics and atmospheric dynamic, climate dynamic modeling. But Jerry went to one of my talks and cornered me after the talk and persuaded me to develop a model for the Earth's mantle convection. And then persuaded me to teach one of his new students how to use that model. That was David Berkovici. And a few years later, another student, a young guy at Caltech, Paul Tackley. So Jerry's been very instrumental in guiding young people. These two guys have done much more significant research in mantle convection than I have ever done. And therefore, what I did is I sort of gravitated closer to the center of the Earth. I worked with Paul Roberts on developing models for the core dynamics and the geodynamo, which is what Jerry's going to be speaking to us about today. He's going to be talking about what we know and actually, more importantly, what we don't know about the Earth's core, the uncertainties in material properties, the amount of heat that's coming out of the core, and the dynamics of the fluid core and the solid inner core. So now I'd like to present Lieutenant Gerry Schubert, who is going to tell us about a geophysicist's journey to the center of the Earth.
Well, thank you very much, Gary, for the introduction. The title of this talk will, I think, become more apparent later in the lecture. But right now, let me just mention that this year's Birch lecture falls on the 50th anniversary of the publication of Francis Birch's classic paper called Elasticity and Constitution of the Earth's Interior. In fact, there was a special session this morning of the same title in the mineral physics session. So it's always an honor to be invited by one's colleagues to give a lecture such as this, but in this golden anniversary year, I think it's even more special. Birch's 1952 paper was the definitive statement of what the Earth was like in its interior, from the upper mantle to the core. It was based mostly on data from seismology and mineral physics. And although it was written 50 years ago, it had things basically correct and was filled with quite remarkable insights. As Gary mentioned, I will spend a lot of my time today talking about the core, although not exclusively dealing with the core. I will tell you what a number of things that Birch said in his 1952 paper, and I will summarize what we know today, or what we think we know today. One of the most exciting and puzzling discoveries about the core in recent years, its apparent seismic anisotropy in the inner core. I'll spend some time on this topic. I will speculate a great deal about possible structure in the Earth's outer core, which I know many of you will regard as highly implausible. I'm going to point out some problems about understanding the Earth's heat loss and the amount of heat flowing out of the Earth's core. And this problem is also connected with difficulties in understanding the age of the inner core and the operation of the geodynamo. I won't spend much time talking about the mantle. It was the focus of last year's excellent Birch lecture by Louise Kellogg, but I will say something about a subject that has interested me very much in the last year or so, and that's the subject of superplumes. And I will be proposing that perhaps superplumes don't really exist, but instead that they might be plume clusters. So I embark upon this list with some trepidation, because I know that there are many people in the audience who are more expert than myself on these various topics, but I'll stick my neck out anyway. I think it's appropriate to dwell on the core these days, because the core has taken center stage in recent years in the research interests of many of us. The core has not only fascinated scientists, but it's also fascinated non-scientists. It's been a favorite subject of science fiction writers, and arguably the first great piece of science fiction was Jules Verne's Journey to the Center of the Earth, which was published in 1864. And some remarks I'll make later may justify the classification of that book as really the first great piece of science fiction. There have been lots of other books on the Earth's core. One was written by Edgar Rice Burroughs of Tarzan fame, published in 1922, called At the Earth's Core. And even Hollywood has gotten into the act with a soon-to-be-released movie called The Core. And I think now that that is going to happen, we can all be comforted and assured that we've been giving our attention to the right subject. So let's get into some science here. This is figure 1 in Birch's paper. And it's a plot of seismic velocity versus depth. And you'll notice that nothing is shown here regarding the shear velocity in the inner core. If you go to a more modern version of this figure, you will find the shear velocity plotted on this diagram. We know the shear velocity from normal modes. The detection of shear wave propagation through the inner core is perhaps still a little controversial. Even though Birch didn't plot the shear wave velocity in his figure 1, he did estimate the speed of shear waves in the inner core. And he did this by estimating the value of Poisson's ratio in the inner core from the compressional wave velocity and from the ratio of the bulk modulus to the density. And then he used this value of Poisson's ratio with the V sub p value to estimate the shear wave velocity in the inner core, getting this number, which I find remarkably close to the generally accepted value of shear wave velocity in the inner core today. The high value of the Poisson's ratio is one of the unusual properties of the inner core. It's about a factor of 2 larger than the Poisson's ratio is everywhere else in the solid Earth. We know that the inner core is solid, and Birch also reached that conclusion. And when people write papers today and they want an early reference for this fact, they usually give credit to Birch's 1952 paper. What's perhaps less well known is that Birch actually hedged his bet on this matter, and he wrote, and this is a quote from his paper, "But it is possible that the inner core is a new phase of iron and is liquid like the outer core." So that particular sentence is not usually one that people today dwell upon when giving credit to Francis Birch regarding the solidity of the inner core. So what other things do we know about the inner core today that Birch didn't know? We know the density jump at the inner core boundary, and this is a number that we'd like to know even better. We know something about the Q of the core. The outer core is fairly non-dissipative. The inner core is dissipative, and especially so near the inner core boundary. We know that the inner core, or we think we know that the inner core is seismically anisotropic, with the north-south direction being faster than the east-west direction. This is a figure that I borrowed from Ken Krieger, and it shows some more details about the anisotropy of the inner core. If we take all these findings as truth, certainly the anisotropy of the inner core is very strange, and it's getting probably even stranger with time. First of all, the inner core has an isotropic layer at its outer part, and this layer is not of uniform thickness. It's fatter in one hemisphere than in the other. So hemispheric asymmetry in the thickness of the isotropic part of the outer core. And not only is this region hemispherically asymmetric in its thickness, but things like seismic velocity and Q are also different in these two hemispheres. And it's only the lower part of the inner core that shows strong anisotropy. The situation is perhaps even more complicated than appears in Ken's slide. There's been a recent paper by Ishii and Zwansky who have proposed that there's something called the innermost inner core. And this is a small part of the inner core. It's the spherical region, about 300 kilometers in radius. And the thing that distinguishes it is that it has different anisotropic characteristics from the rest of the inner core surrounding it. The direction of the slowest wave speed in this innermost inner core is about 45 degrees from the rotation axis, whereas surrounding this innermost inner core, the slowest direction is 90 degrees from the rotation axis. So the question is, How do we explain these puzzling observations of inner core anisotropy? One way to do it might be through partial melting in the inner core with alignment of melt-filled cracks. This explanation may be true, but there have been other studies, both theoretical and experimental, that show that partial melting isn't necessary to explain either the anisotropy or the high Poisson's ratio or the dissipation. Instead, we might seek an explanation in terms of the properties of hexagonal close-packed iron, which is generally believed to be the major constituent of the inner core. Although we heard a talk this morning by David Price, who raised the possibility that maybe this might not be true and that some other structure of iron might exist in the inner core. The HCP iron, if we accept it as constituting the inner core, is a relatively anisotropic form of iron, and the anisotropy in this hexagonal close-packed structure is determined through the orientation of this C axis. There are first principle calculations that were published by Steinle-Neumann et al., which show that the elastic constants of HCP iron vary strongly with temperature. You can see the strong variation with temperature of the various elastic constants. And under core conditions, under the temperature and pressure that we expect in the core, it seems possible, according to these calculations, to match the bulk modulus and the shear modulus of HCP iron, and also to explain the anisotropic seismic velocities. But at high temperature, the compressional wave velocity, which is this solid curve here, has its slowest direction not along the C-axis nor at 90 degrees to it, but at some other angle, perhaps something close to 45 degrees. So by appropriately aligning the axes of HCP iron through either solidification by a variety of mechanisms, or perhaps by deformation brought about by different stresses that could be exerted on the inner core, perhaps that's a way to explain the anisotropy. But I think that, one thing seems for certain to me is that certainly one sense of alignment is not going to account for all the complexity that we're presently faced with in explaining the anisotropy of the inner core. So we're left with a number of questions. Why is the upper inner core isotropic and the lower inner core strongly anisotropic? What accounts for the inner core hemispheric asymmetry and seismic velocity and attenuation and then anisotropy? And what explains a change in the alignment at the outer boundary of this innermost inner core? Birch offered us some advice in his 1952 paper. He said, it is essential that the best seismological solutions be sought without reference to their physical significance. It was an interesting statement that one might think about for some time. He also went on to say that conceivably we might need to look beyond seismology to figure things out. So those of us who are not seismologists, I guess, have some hope that maybe we can contribute towards understanding the processes going on in the deep earth. I think we're definitely following Birch's advice, at least as far as the inner core is concerned, because we are coming up with seismological models which are really challenging our ability to come up with physical explanations for them. Another thing that we know about the inner core that Birch didn't know is that it may be rotating more rapidly than the surrounding mantle, but maybe not. There's been a lot of studies in recent years about this phenomenon, and I think it's safe to say that the present consensus, if there is one, is that if there is any rotation of the inner core with respect to the mantle, that it certainly must be very small. Birch concluded that the outer core was a homogeneous liquid. I think that was as far as the liquidity of the outer core was concerned, that was a pretty safe assumption to make. At the time, there were lots of lines of evidence prior to Birch's paper from analysis of Earth tides and the Earth's rotation and the secular variation of the Earth's magnetic field. These all indicated that the outer core was liquid, but of course we had to rely on seismology for the definite answer, and the absence of seismic shear wave propagation through the outer core was the clincher here. Now, I would like to suggest, at the risk of embarrassment, that maybe we should start to think a little more about this issue of outer core homogeneity, because the dynamics of outer core convection are such that there might be ways to preferentially concentrate light material in different parts of the outer core, or perhaps bring about some other changes that could affect seismic waves in the outer core. The reason for this is shown in this cartoon, which oversimplifies the nature of convection in the outer core, but illustrates some of the basic principles involved. There is something we call a tangent cylinder in the outer core. It's a cylinder whose axis is parallel to the rotation axis. It's tangent to the inner core on the equatorial plane, and it divides the outer core into two distinct dynamical regimes. Outside the tangent cylinder, one has basically these two-dimensional convective columns or rolls, whereas inside the tangent cylinder there are more complicated three-dimensional columnar plumes. And the real convection going on in the outer core is incredibly more complex than suggested by this cartoon, but the fact remains that there will be a significant difference between the dynamics inside the tangent cylinder and the dynamics outside the tangent cylinder. My colleague at UCLA, John Arnaud, has performed a convection experiment which illustrates some aspects of this very nicely. What he's done is considered a flat plate, and a portion of that flat plate in the shape of a circle is heated. So one gets convection above this circular portion of the flat plate. And there's fluid above the plate. There's like a hemispherical cap above this, which one can think of as simulating the core mantle boundary. And this whole apparatus is rotating. He injects dye above the heated circular region of the plate. And this dye outlines the convective plumes that get set up. And one can see in successive time steps how this dye extends above the circular region of the heated part of the plate, and eventually fills up this tangent cylinder. There's a virtual cylinder here. There are no walls that keep the green dye inside this tangent cylinder. Now, in this experiment, the dye actually doesn't remain inside the tangent cylinder indefinitely, but it actually gets mixed outside the tangent cylinder by what we refer to as baroclinic disturbances. And these baroclinic disturbances are shown in another experiment by Arnaud et al. In this experiment, one is looking down on the system instead of looking from the side, and one can see the development of these wave-like baroclinic disturbances. And these are the same types of things that we see in weather patterns in the Earth's atmosphere, where we have planetary scale baroclinic waves. In this experiment by Arnaud et al., there's a thermal wind that gets set up at the tangent cylinder boundary that actually shears off the instability and actually limits outward radial mixing from the tangent cylinder. So these are laboratory experiments, and they're not conducted at parameters appropriate to the Earth. So the real question is, what happens to the light element in the Earth's outer core? We know that as the inner core solidifies, that light material is injected into the tangent cylinder. The question is, does it remain there? Does it stay in that tangent cylinder, or is it mixed uniformly throughout the outer core? There's a argument in fluid dynamics called thermal wind balance, in which one balances the Coriolis force against horizontal pressure gradients. And that thermal wind balance has been used, along with other arguments, to conclude that any seismically observable density anomaly would not be able to be maintained inside the tangent cylinder, because it would just require much too large velocities in order to do that. Perhaps one might be able to set up a different kind of dynamic balance involving viscous or magnetic stresses on the tangent cylinder boundary, which might be able to confine this density anomaly to this tangent cylinder. I've been looking into that. I must confess that preliminary results doesn't show that to be a very viable option either, but I haven't totally given up yet. I think with a few exceptions, seismologists are not following Birch's advice when it comes to the outer core. And let me remind you of that advice. It is essential that the best seismological solutions be sought without reference to their physical significance. So I think if you want to follow Birch's advice, then a seismologist should not worry a priori about what dynamicists say is possible or not possible about the outer core, but they should look for the best seismological solution to their observations. One possible exception to this is this paper by Romanowicz and Bréger, in which it is shown that almost all normal mode splitting data for modes sensitive to Earth structure can be explained by a tangent cylinder anomaly. So maybe there is no such anomaly, but if there is, then this might provide an alternative explanation for the fact that waves that travel in the north-south direction apparently travel faster than waves traveling in the east-west direction, so that one has an alternate explanation for inner core seismic anisotropy in terms of outer core structure. So this is very speculative, and maybe in the end it won't prove to be valid, but I think it's something worth considering. I don't have to discuss time to discuss many of the insightful things that are said in Birch's 1952 paper. I just want to point out a couple things he said about the mantle now, and about phase changes taking place in the mantle, because in my own career I've spent a lot of time thinking about mantle phase changes and how mantle phase changes might affect convection. And although he didn't really carry this very far, Birch did notice and say that phase changes in layer C, which is the transition zone, may affect mantle convection. And he also said that deep focus earthquakes may be related to phase changes in the transition region. And both these ideas have received lots of attention in recent years. So I'd like to next go on to discuss something about the Earth's heat flow. And this was a question that Jules Verne was thinking about in 1864. After all, it wouldn't do if it was too hot down there to journey to the center of the Earth. Now there are lots of scientific arguments I found in Jules Verne's book, which are actually, pretty decent arguments. And probably everyone here has read this book, but if you read if you read it in English and you read a translation, you may not have read a version that did justice to these scientific arguments that were used in discussing the Earth's heat. So I found these arguments to be amusing and interesting, and some of them are surprisingly close to some of today's discussion. So that I'd like to quote a few of them for your diversion and entertainment. And I got my version of Jules Verne's words from a translation by William Butcher that was published only fairly recently in 1992. So first, Verne argued about the possibility of extrapolating the near-surface temperature gradient to great depths. And to make it easy for you, I'll read these few words. Yes, it is well known that the temperature increases by approximately 1 degree centigrade for every 70 feet you go below the surface of the globe. So I think only the British could confuse degrees Celsius with feet. Now, assuming that this ratio remains constant, and given that the radius of the Earth is about 4,000 miles, the temperature at the center will be well over 200,000 degrees. And I checked this number, and it turns out to be pretty correct. The substances at the Earth's core exist, therefore, as white-hot gases. For even metals like gold or platinum, even the hardest rocks cannot resist such a temperature. And I've left some words out, so it might be a little difficult to follow this, but he goes on later to say, why should it not be the same for the internal heat? Why at a certain depth should it not encounter a limit that cannot be crossed, instead of reaching the point where the most obdurate minerals liquefy? So what Verne was arguing was that you really can't extrapolate the surface temperature all the way down to the center of the Earth. We wouldn't think of doing that today, but Verne was basically right in thinking that maybe the temperature gradient does fall off with depth, and maybe it in fact goes to zero and we reach a limit of temperature. So there's a second argument which I think is less sound. Again, quoting from this book, well, Axel, I can tell you that real scientists, amongst them Poisson, have proved that if a temperature of 200,000 degrees actually existed inside the globe, the white-hot gases produced by the fusion of the solids would acquire such force that the Earth's crust could not resist and would explode like the walls of a boiler under steam pressure. Poisson's opinion, Uncle, that's all. This third argument is really pretty good because we still use the density of planets as a major constraint on their composition and structure. That's all we have to say. It's all we know, for example, about Mercury, and it was all we knew about the Galilean satellites prior to the Galileo mission. So using density to say something about interior composition and structure is, a really important scientific argument today. So he said, agreed, but it is also the opinion of other distinguished geologists that the interior of the globe is not formed of gas, nor of water, nor of the heaviest rocks that we know. The reason is that, if it were, the Earth would only weigh half as much as it does. So Verne actually knew that we had to have something heavier than even the heaviest rocks at the center of the Earth. Oh, you can prove anything you want with figures. Verne discussed the secular cooling of the Earth. He said, is it not true that the number of volcanoes has considerably decreased since the first days of the world? And if there is indeed heat in the center, can one not deduce that it is also tending to diminish? Uncle, if you're entering the realm of suppositions, there is nothing more I can say. We, in fact, forgot for a number of years about secular cooling, and it was argued until somewhat recently that the Earth's heat flow is in equilibrium with the amount of heat produced by radioactivity in its interior. So Verne realized that secular cooling was important. He falsely argued against the liquidity of the core. Well, Sir Humphrey came to see me as he was passing through Hamburg. Amongst other things, we had a long discussion about the hypothesis that the innermost inner core of the Earth was liquid. We both agreed that a molten state could not exist, for a reason to which science has never found a response. What reason is that? I said, slightly stunned. Because a liquid mass would be subject, like the ocean, to the moon's attraction, thus producing internal tides twice a day, which would push up at the Earth's crust and cause regular earthquakes. Now, the idea of tidal stresses causing regular earthquakes is certainly not a ridiculous idea. So finally, we'll finish up with Verne with his conclusions here. You see, Axel, the state of the central core has produced various hypotheses amongst geologists. Nothing is less proven than the idea of an internal heat. In my view, it does not exist, could not possibly exist. All this must be maintained totally secret, so that no one else has the idea of discovering the center of the Earth before us. If people knew of the document, a whole army of geologists would rush to follow in Arne Saknussemm's footsteps. So apparently Verne didn't think too highly of the scientific integrity of geologists. So what do we know about the Earth's heat flow? Or what do we think we know? We think we know that 44 terawatts of heat flows out of the Earth. But I would remind you that we haven't measured it. We really have, we've calculated it. It's based on a theory. We really haven't measured the total heat coming out of the Earth. We know that about 7.5 terawatts is due to radiogenic heating in the continental crust, but once again, that's a number we haven't measured. So if you subtract these two numbers, you get 36.5 terawatts, which is flowing out of the Earth's mantle. And this amount of heat can come from the core, or it can come from radiogenic heating in the mantle, or it can come from secular cooling of the mantle. What we'd like to know is what these individual contributions are. Now, cosmochemists tell us that about 20 terawatts of heat can be produced by radioactivity in the Earth, and that includes the continental crust. So, if you take 20 terawatts and you subtract this 7.5, and get 12.5, and then you subtract 12.5 from 36.5, you come up with 24 terawatts that must come from the core or from secular cooling of the mantle. Now, 24 terawatts is a lot of heat. It's basically more than half the amount of heat that's being lost at the surface. And it has to come from one or two places, unless we want to fiddle with radioactivity concentrations. It must come from the secular cooling of the core, of the mantle, or it must come from the core. So how much heat is flowing out of the core? We can get an estimate of this by calculating the heat conducted along the core adiabat. We believe the core to be adiabatic at present. We need to know either the Gruneisen parameter, this gamma, or we need another way of saying it is that we need to know the thermal expansion coefficient. Of course, we need to know other things like the thermal conductivity of the core and the temperature of the core in order to make this calculation. We know most of these numbers fairly well today, although we don't know them with, great certainty. There's still some uncertainty in these numbers. I choose to make this estimate using this set of numbers from a paper by Orson Anderson. And if you plug those numbers into the formula, you get 7 terawatts of heat that is flowing out of the core by being conducted along the adiabat. Now, that's not the total amount of heat that's flowing out of the core, so it's a lower bound. There's convection going on in the core, and more heat may be flowing out than this 7 terawatts. So, maybe a number like 9 or 10 terawatts is more like the amount of heat being transported out of the core. It also means if you subtract 7 terawatts from the 24 that was on the previous view graph, that 17 terawatts has to be attributed to mantle secular cooling. 17 terawatts you could compare with 20 terawatts associated with radioactive heating inside the Earth, and you can conclude that those amounts of heating are comparable. There are some difficulties in reconciling these numbers with a lot of generally held beliefs up till the present. And there are several different alternatives we have to do that. One alternative is to say that there's more radioactivity in the mantle than cosmochemists think there is. In other words, the Earth might have a superchondritic abundance of radioactive elements. Well, maybe the cosmochemists are right, and another way to understand these numbers is that secular cooling of the Earth's mantle contributes just as much as radioactivity, or even more, to the Earth's heat loss. Again, the cosmochemists may be right, but the core might contribute a great deal to the Earth's heat loss, and that might require some radioactivity in the core. And the third, another possibility, of course, is that the cosmochemists are right, and you just want to divide the additional required heat between the core and the secular cooling of the mantle. Now, these numbers imply some problems with the age of the inner core and the operation of the geodynamo. If you allow the Earth to be cooling at the rate of 7 terawatts, you can calculate that at this rate of cooling, which again I emphasize is a minimum, you could remove enough heat to freeze the inner core in only 440 million years. And this may be a problem because it says that the inner core might be a fairly young feature of the Earth. Another way to think about this problem is that if you imagine that this cooling rate of 7 terawatts operated over the age of the Earth, the entire age of the Earth, then the Earth's entire core should be essentially solidified today. So the question is, can the inner core be only a few hundred million years old? And the answer to that might be no, if you believe that the freezing of the inner core is necessary for the dynamo to operate. We know the Earth's magnetic field has been around for about 3 billion years, and many people believe that the freezing out of an inner core is necessary for that dynamo to operate. The problem with the age of the inner core has been discussed by a number of people. Bruce Buffett talked about it earlier today at this special session on the Earth's constitution. And in the literature, Stefan Labrosse and David Gubbins have also been talking about this problem, and I should also mention Francis Nimmo discussed this problem earlier today in that same session I've been referring to. So where do you get the energy from the core to maintain an adiabat over several billion years without freezing the core? There are some possibilities, and these possibilities include the fact that the core might be subadiabatic or might have been subadiabatic in the past. And another thing that helps is putting radioactivity inside the core. And it wasn't so long ago when talking about radioactivity in the core was basically a no-no. But today I think it's gaining plausibility, and you'll find lots of people talking about the possibility of radioactivity, say potassium-40 or even uranium and thorium being inside the core. So sort of reaching the end of my time, let me just spend a couple minutes talking about superplumes and plume clusters. Seismic tomography has revealed the existence of two broad seismically slow regions in the lower mantle under the south central Pacific, and under Africa. And many people refer to these regions as superplumes. Romanowicz and Gung they published a paper recently in Science this year, and they found that zones of high seismic attenuation in the upper mantle lie above the lower mantle low velocity regions. And they suggested that these superplumes could extend continuously through the mantle from the core mantle boundary all the way to the lithosphere. And I just want to suggest to you today that these so-called superplumes might instead be dense clusters of smaller plumes. And this is a figure that was in Romanowicz and Gung paper. And these top two panels show the degree 2 variation in attenuation in the upper mantle and the shear velocity in the lower mantle. And you see that, one lies above the other. There's just a cartoon illustrating the idea that instead of looking at a superplume, we might be looking at a plume cluster. And certainly if you look at a plume cluster with blurry seismic vision, it might appear to be a superplume. The arguments for plume clusters include some seismic data that show that the superplumes under Africa and under the South Central Pacific actually consist of smaller structures. There are also dynamical arguments to suggest that plumes that originate as instabilities from the core mantle boundary are likely to be much smaller in size than these superplume regions. And this is a seismic S-velocity map near the core mantle boundary produced recently by Guy Masters, and it may not show up so well from where you're sitting, but it shows that there are really multiple centers of seismic structure in the Pacific. And if you count these things, and if you could see better what the structure is, you might count 6 or 7 centers of activity. And if you look beneath Africa, you are going to see at least 2 such centers. So even at present seismic resolution, there are at least 2 superplumes beneath Africa, several in the Pacific. And as seismic resolution improves, I think that we might even be able to see smaller structure. I think I probably won't have time to go through all these other arguments, but you can put together a lot of dynamical arguments that plume clusters are a common feature of thermal convection, especially high Rayleigh number thermal convection. Plume clusters often form when there is variable boundary topography or heat flow or associated with compositionally dense material. And plume clusters can also occur through the concentration by externally driven larger scale flows or by plume entrainment. Plume entrainment can lead to clustering, and also external flow can lead to clustering. And the effectiveness through which that occurs depends on the ratio of the Stokes rise velocity of the plume head to the external velocity, U sub m, that might be driven by plate motions or some other large-scale circulation in the mantle. If this ratio is small, you suppress plume formation. If the ratio is large, there's little effect on the plumes. If the ratio is order 1, then the plumes can be advected towards a large scale upwelling. and the fact that the plumes have their own rise velocity prevents them from being fully captured and developing into a superplume, and you get a plume cluster instead. And beneath Africa and the Pacific, there's likely to be global scale upflow and perhaps a tendency to gather smaller plumes into these regions. Okay, I'll go to my conclusions now. I think we perhaps don't understand the seismic anisotropy of the inner core yet. I think the seismologists may have to clarify that for us. We're not in a position yet where that's perhaps fully understood, and we certainly don't understand things from a physical point of view, how such anisotropy can come about. I think we should follow Birch's advice and explore the possibility that there might be seismic structure in the outer core. We certainly have to change our view about the possibility that there might be radioactivity in the Earth's core in order to solve some problems associated with the age of the inner core and the operation of the geodynamo. And although I didn't get a time to present a really convincing argument to you, I don't think that there are really superplumes in the Earth's mantle. I think what we're dealing with are just broad upwellings and plume clusters associated with these regions. So I'd like to acknowledge a number of colleagues who are kind enough to send me slides that they prepared for their own lectures. I found them very helpful, although in the end I only used a few of them. And I'd also like to acknowledge discussions with all the people listed here. They were extremely helpful in clarifying ideas for me. But I do take responsibility for all the outrageous things I've said here. Thank you.